I went there, but they were already closed. It ended at 2:45.
All right. So this is your home page again. Looks like the class notes weren't up. So if there's something missing here, you can just send me an email, because there's a good chance that I forgot. There might be another chance that I haven't processed the thing yet. But from now on, the class notes should be available. And starting last class, I started to videotape it, and so all the stuff is available on videotape as well. So you can visit our website for all that information. And I think the last thing we did was vector dot product. So today we're going to continue working on vector dot product, and then we're going to discuss lines and planes. So we'll start off with some information that's already been presented, and then throw in a set of properties. And then we'll talk more about the geometry of the dot product and a few implications. There's one more definition after this one also, but let's take a look at and try to remember a dot product. Our prime example for the dot product was how to figure out your grades by figuring out your grade vector and then the weights of the categories. And so we took the dot product of that to get the overall score. But just to remind you, the dot product of two vectors is this sum after you multiply each of the components with each other. And remember that our result is a scalar. So sometimes this is called the scalar product, as opposed to a vector product like the cross product, which we won't do in this class. So paired up with the addition of vectors, we can take a look at the dot product properties. The dot product is commutative. The distributive property holds. Now this is some form of associativity. It's associative with a scalar multiplication up on in front. What they're saying is that if you scale one of the vectors and then you dot it with another vector, it's the same thing as dotting the two vectors first and then scaling the result. And then here's another property where if you take the dot of itself, then it's going to be bigger than or equal to 0. And the only way that this is going to ever equal to 0 is that if they're both equal to 0. So as I look through this, there's a commutative. There's this form of associative when they're playing around with another scalar, but I don't seem to have this associative property of the dot product. U dot V dotted with W is equal to U dotted with V dotted with W. So this is an associative property, right? This looks like it's an associative property. And is it clear that it's not on this list here? And so there's an associative property here, but it's not the same as these three vectors. This is two vectors and a scalar. So what's wrong with this? Why is this not equal? So when you dot two vectors, you get a scalar, and then now this is no longer a dot product. This is a scalar multiplication, and that clearly wouldn't work in this scenario. Okay? So the associative property for a dot product, not only does it not equal, but it doesn't even make sense. So there is no associative property for the dot product. The best they can do is the scalar multiplication of dot of two vectors. Okay, which would come in handy for us sometimes when we're proving things. Okay, any questions? Yes?
So when you say scalar, that means that it's going to be a number, right?
Yes.
Number, right?
Yeah. So for us, a scalar is a number. Realistically, it could be a real number or it could be a complex number. But we're not going to be dealing with complex numbers.
And if the vectors are different dimensions?
Yes, because the vectors, yeah, the vectors have different dimensions. Well, the vectors here, u, v, and w are all vectors in the same dimension. So you can only take the dot product of vectors in the same dimension. Or for that matter, you can add, subtract, and all that stuff if they're all in the same dimension. Okay? Anything else? All right. Let's take a look at another definition of something to do with vectors, and that is the length or the norm. Now, I don't know if I want to use the word length necessarily. But geometrically, that's what it is. It's actually the length of the vector. But another word for this, or the word that we should be more familiar with, is to use the word magnitude. Sounds cooler. It has more syllables. Because the word length, sometimes in computer programs, the word length means how many entries do you have in that vector. So we would normally look at it like if this is a vector in R6, then the length would be 6 according to some computer programs. So the magnitude is something else that's a little bit different. It's what's going to be calculated. So the magnitude is denoted with double bars, and most of the time I'll be using double bars, although sometimes I use single bars. But let's think about a single bar length. What does a single bar look like? Absolute value, right? And what is the absolute value anyways? It's the distance from something to something. So if it's just a number, then it's distance from the origin. So really, it's the same thing. So the absolute value is just a special case of the length, the norm, or the magnitude, except it's in one dimension. So in one dimension, let's call it R, length of a number, this is alpha, is the absolute value. So it's the same thing. And so once in a while, if I'm in a rush or something like that, I'll just put single bars for a vector in Rn, R3, R4, whatever. If I put a single bar on that, on a vector, it's assumed to be the length of the magnitude. So we should think about length and absolute value, or magnitude and absolute value, to be the same thing. And also geometrically, before we go on to the theorem here, geometrically, whether you're in 2 or 3 dimensions, if you have a vector from 0, 0 to the point A, comma B, if we were just to look at this as a line segment, just a line segment, do you remember the length formula in geometry where you have 2 points? It'll be what? The square root of A minus 0 squared plus B minus 0. Yeah, the distance formula. So just the distance between these 2 points would be this formula, which is pretty much the same thing as the definition of the length or magnitude. So it is exactly the same thing. Okay, in fact, this distance formula, I forgot what it was called. Would be useful for us if we're looking for the length of a vector that's connecting between 2 points, and we'll just find the distance between 2 points, and then we'll find the length or the magnitude. Okay? So, a couple of important properties. The first property says that it's the length has to be, well, actually, in the previous slide over here, we saw that this thing is bigger than or equal to 0. And you see that u dot with itself is just the square of the length. So if you take the length and you square it, you're going to get the same thing, u dot with itself. And we know that it's going to be bigger than or equal to 0 because it's a length, it's a magnitude of thing. And then it's only going to be equal to 0 if you have a 0 vector. And then another important property here is that if you multiply it by a scalar, it's the same thing as taking the absolute value of the scalar. And so this is the absolute value symbol here. Okay? And let's prove the second one just for the sake of proving something. Because this class is supposed to include proving things also, although it's only a 3-unit class. Don't have too much time to do this stuff, but let's do this one. We want to find the magnitude of C, a scalar C, multiplied by a vector V. So let's assume that the vector is in Rn. So let's assume that the vector is V sub 1, V sub 2, dot, 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 V sub n. So these numbers, V sub something, are all scalars. And then there's n of them, so they fit into these n components. And then we're going to take a look at C times V, which is C times this whole thing. I'm just going to put star here because I don't want to rewrite it all over again. But that means C is going to be distributed among each of these components. So CV1, comma CV2, comma dot, 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 comma CVN. So that's my scalar multiplied across each of those components. Now I want to take the magnitude, so I have a choice of either taking the dot product and taking the square root, or just, that is basically the same thing. So I will do that. I will say that this, according to the formula, is a square root of CV1 quantity squared plus CV2 quantity squared plus dot, 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 plus CVN quantity squared. So all that under square root, and I see that they have something in common. They have a factor of c squared that I can take out of all the terms. And in fact, I could take it out of the square root. But before I do that, I'll just be a little bit careful. I'll call it c squared that I'm taking out with a square root right now. And then before I cancel the square roots, I just want to talk a little bit about what that means. But after I take a c squared out, I just have a v1 squared plus v2 squared plus dot 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 plus Vn squared. Okay? So, let's talk about the square root of c squared. Is this a plus and minus c, or is it just a plus c? This is just a plus c. So that means if c was negative to begin with, when you square it first and then take the square root, it's going to end up being positive. So this is always going to be positive. So it's always positive even if c is negative to begin with. It's going to become positive. That just means that's the absolute value, right? You just make everything positive. And on the right-hand side, what's left here is, well, according to just the definition again. So that's just the absolute value or the magnitude of v. Okay? So I went from, oops, I should have said that this here, starting here, was the magnitude of CV, and that's equal to this, which is equal to this, which is equal to this, and that's where we ended. That's what I wanted to prove. So what do I put? EG. Quad eros demonstratum. Okay, so that's done. So that's the proof of that. Okay? Any questions? All right. So that's the magnitude. I guess before I talk about this, why don't I take it out first? Let's do a simple problem of finding the length of the vector 2, 1. Okay? Let's find the length of this vector 2, 1. So what is the length of this vector? Okay? Square root of 2 squared plus 1 squared, which is 4 plus 1, square root of 5. So the length of this vector is square root of 5. So if I were to draw this vector, I'm going to get the length of this is square root of 5. Now, what if I want a vector going in the same direction as this, but I want this vector to have length 10? So W is a vector, same direction as V, but has magnitude equal to 10. So how are we going to find W? The thing that's kind of what I would think about really quickly, without, if I didn't really think about this too hard, is I would just multiply V by 10, right? So how about W equals 10V? Is that going to work? Let's see. So 10v, so this is 20 and 10, right? Let's check by finding the magnitude of w. Magnitude of w. Okay, so these are my components now, 20 and 10. So magnitude of w is the square root of 20 squared plus 10 squared. What's 20 squared? 400 plus 100, square root of 500. And does that simplify to a magnitude of 10? No. What is this equal to? 100. I can take 100 out, right? So that's 10 squared. So this is 10 root 5. Okay. So that didn't work for us. The magnitude of this does not equal to 10. In fact, it's equal to 10 root 5, and root 5 was the magnitude of the original vector v. So the idea of multiplying something by 10 sounds good, but it didn't work. So what is special about multiplying something by the number that we want it to be scaled to? What has to be special about that vector? It has to have a unit length. If v had a unit length to begin with, then we would have a better chance of multiplying the unit vector by 1 so that it scales to 10. So here is the piece of information that I copied and erased, and now I'm going to put it back. It turns out that a unit vector is a vector of length 1, and the way you can find a unit vector is to take your vector and divide it by, which means really multiplying by the scalar 1 over the magnitude of that vector. So we didn't formally define a division of vectors, but we did define a scalar multiplication. So you're essentially scalar multiplying by the reciprocal of the magnitude. So this notation, the divide notation, is really multiplying by the reciprocal. Because we have scalar multiplication, but we don't have scalar division defined or anything. So what that means is that you're just going to take each component and divide by the magnitude. All right. So let's make our v vector first. Let's make that into a unit vector, and we do that by multiplying by the reciprocal of the magnitude. We already got the magnitude 1 square root of 5, right? So that's the magnitude. And so if we multiply this 1 over the magnitude by the vector, then let me write it out. Then we have a unit vector in the same direction as v. Now, to get the vector that we actually want, we simply take our unit vector and multiply that by the length that we want this to be. So we want this to be of length 10, and we'll multiply that by u. So what does that mean? That means I'll have 10 times 2 root 5 over, and then 1 root 5. So 20 root 5 and 10 root 5. Okay? So the only thing left to do here is to check to make sure that the magnitude of w is in fact equal to 10. Check yourself. Okay? it is going to equal to 10, but you check it yourself. I'm not going to do it. Questions? So there's some value in knowing how to find a unit vector going in a particular direction. Okay? All right. Let's see. Yeah, finding unit vectors will become really important for us later on. So this has to hopefully become second nature as you do more and more of these problems. There's two inequalities that are kind of important to mention. I don't know how much of this we'll be doing in this class, but I'll just mention it then and not really talk too much about it. So the Cauchy-Schwarz inequality is defined by a dot product. If you take the dot of two vectors and the absolute value of that is going to be less than the absolute value or the magnitudes of the two vectors being multiplied. I think that's an interesting theorem in math, and it could be used to prove some of the theorems that we're not really going to look at in detail. So I'll just mention it. And then the triangle inequality, if you remember, the sum of two vectors makes up one of the diagonals for the parallelogram that the vector spans. And so this is the triangle inequality has a nicer geometry that you can actually visualize, and it does use a triangle. So it says the length of two of the sides has to be bigger than or equal to the length of one of the sides of the triangle. So if you just picture a triangle, you can think about that, how it works out. And there's a possibility of this thing being equal to each other, and they would equal to each other if you actually don't have a triangle, but you have two lines that are going in the same direction. Yeah, you can think about that too. All right. So that was mentioned in the book, so I'll mention it. And the distance, between two vectors, this one I'd like to say more than just to mention. But if you have a u and a v vector, the distance between these two vectors would be the distance between the heads of those two vectors. And that would be basically the magnitude of the difference between u minus v. So u minus v, if I have it in this order, remember subtraction is not commutative. So u minus v is not the same as v minus u. So u minus v is a vector between the heads of u and v. Which way is my arrow pointing? Towards u or towards v? My arrow is pointing towards the first one here. Head minus tail. So in this case, it would be pointing towards u. Okay. The thing about this is that if you take the magnitude, it doesn't really matter which way it's pointing. I just want the length of it. So it didn't matter whether the u was first or the v was first, but in some cases it might matter which way your vector is pointing. So we want to just make that clear. All right. So the distance between the heads of two vectors is really just the subtraction vector, and find the magnitude of this difference vector. So find the difference and then take the magnitude, then that's really what you have. So if you look at this as just a couple of points, V1, V2, U1, U2, you go back to that distance formula and find the difference between find the distance between these 2 points, and that's going to be your magnitude of the difference. Okay? All right. So, a more interesting result, I don't know if I should call it result, because some textbooks define the dot product differently from the way we define it. We define it using, that scalar sum of the products of the components. But some books define it this way, so I don't know if in your book if this is also called a definition of the dot product. But here they're not defining the dot product, they're more defining the angle between the 2 vectors. But this is really an important geometrical fact and also used a lot in physics and finding force and things like that. If we rearrange this, U dot V is equal to the magnitude of U times the magnitude of V times the cosine of theta. And now what's theta? Theta is the angle between the vectors U and V. So if you were to visualize those 2 vectors and you want to find the angle between them, that's going to be defined. That's going to be your defined theta angle. And the cosine of that is involved in this equation. So from here, we get a special property because there's a couple of angles that are kind of special for us, like 0 and pi over 2 and stuff like that. What's cosine of 0? 1. So what's cosine of pi over 2? 0. Okay. There you go. Pi over 2, what's pi over 2? That's 90 degrees, right? That just means that 2 vectors, V and, if this was pi over 2, that means the 2 vectors are perpendicular. So cosine of pi over 2 again was what? 0. So that means the dot product of 2 perpendicular vectors is 0. So that is an important fact. It should be I don't know if it's a property or a fact that's coming up. I don't know if this should be called a definition either. But if 2 vectors are perpendicular, another word for that we'll be using is orthogonal. If 2 vectors are perpendicular, then the dot product's equal to 0. And that's easy enough to justify because the cosine of pi over 2 is equal to 0. Okay? All right. Let's I want to take a look at pictures, but before we take a look at pictures, let's see if we need to show anything else here. Projection. Let's do a projection. All right, to discuss projection, I think it might be a good idea to visualize this. What does this mean? What does projection mean? So what we have here is a notation it's important to kind of parse through. You know what I mean by parse? You just go through it and identify the different components and understand what they mean. So this is PROG, stands for projection of V onto U. So notice that this is V, that's your argument, onto U, which is the vector that you're going to project onto. So what does that mean? That means if we have these two vectors U and V, and I project the light coming down here, the shadow that this is going to make, and the shadow, by shadow I mean it's a perpendicular shadow that this is going to make onto the vector U, is going to be a vector here that's going to be the projection. This is a projection of V onto U. Okay, so what we're saying is that we want this vector to be going in the same direction as U, or I want to say same direction. Let me say along the same line as U, because V could be going the other, or U could be going the other way. So parallel would be another good way to describe this vector. The projection vector, the resulting vector, is going to be parallel to U, and it's going to be casting a shadow on this. So this projection vector should be, if it's parallel to U, should be just the scalar multiple of the U vector, right? So the question is, what is that scalar multiple? Well, we could derive it, or, I mean, the formula is here already, so maybe we don't have to derive it. But if you want to derive it, what you would do is you would take a look at this as a triangle. And we'll make use of the fact that they have an angle between them. We'll call that theta. And I wouldn't call this V anymore. What would I call this? The hypotenuse. It's just a minor technicality. I can't call it V. What do I call it? No? The distance, the magnitude of V. So V is a vector. Now if I break this down to just triangle with lengths, I can't assign a vector to that. So I have that vector, and if I want to look for the side here, I can use one of the trig properties, right? Opposite, or this is adjacent. Adjacent over hypotenuse. What do you think of when you think of adjacent over hypotenuse? Cosine of the angle between them is equal to the adjacent side. This is the unknown side over the hypotenuse, which is the length of V. Wait, the cosine of theta, that was a formula from the dot product, right? The cosine of theta is a dot product divided by the magnitudes. So Turns out that the cosine of the angle between them is a dot product between these two vectors, u and v, divided by the magnitude of u times the magnitude of v. So these two things should be equal to each other, right? Let's set them equal to each other. The question mark that we're looking for divided by the magnitude of v. This is where I need to start just using single bars. Equals u dotted with v over the magnitude of u dotted, not dotted, but times the magnitude of v. So it looks like I can multiply both sides by the magnitude of v. And then, so the question mark is equal to this. Hey, looks like I'm done, huh? So that's what should go in the star. Because we're looking for the length of this, right? And this is the length. Should that go in the star? Is that what goes in here? Wait, that looks different. This isn't my complete answer for star here. What? Oh, so because u is not a unit vector, we can't just multiply this by the length of this. We have to make u into a unit vector first. Right? So, let's see. Looks like maybe the projection of v onto u is equal to this thing, u dot v divided by u, the magnitude of u, times u as a unit vector. So remember how to make a unit vector, just divide by its magnitude, right? Well, this is equal to u dot v divided by, well, this is just the magnitude of u squared. It's still not the same as this. Or is it? Still not exactly the same, right? Is it? So I guess if we just say that u dotted with itself is equal to that, is that true? Does the u dotted with itself equal to the magnitude of u squared? Yes. In fact, v dotted with itself is the square root, or the square root of that v dotted with itself is the magnitude of v. So if you imagine squaring both of these, then you're going to get that same thing. Oops. So, I switched the order of v and u. So this is the same thing as u dotted with u, and then the vector u. So now this is a star that goes in here. And that's exactly what they had in the formula. Okay? All right. Any questions? Yes?
The unit vector is the direction, right?
The unit vector is a direction, yeah.
And the other thing is the magnitude.
Well, it depends on where you're looking at. Over here, this is the magnitude that we want. That's the length of this side. And this is the unit vector. Yeah, that gives a direction. So this is the unit vector that gives a direction of u. And then you multiply it by the magnitude, and then we get the exact projection vector that we want. Okay? All right. So there's a few more applications for the dot product, but let's move on. Okay, let's start talking about lines and planes and stuff like that. Let's talk about lines first. I have a graphing program here where I can draw vectors and lines and graphs and things like that. So let's take a look at a vector. Let's call it A. And so in this particular graphing program, if I want to draw a vector, say in standard position, I would draw 0, 0 to say that this is my starting point, and then I end at A, and this is my vector here. Okay? Now, remember the idea of scalar multiplying is that if you multiply something by a scalar, all you're doing is you're stretching it out. So if I let my n go from like -10 to 10 or something like that, if my n values or my scalar values are negative, I would actually be pointing in the opposite direction. And if my scalar values were positive, I would be pointing in the same direction, but it would be stretched out. Okay? So there's this idea of a scalar value. The power of the scalar value is to scale the vector. So what I could do is essentially start off with a vector like 2, 1, and then multiply that by some scalar. And if I multiply that by some scalar like a parameter t or something, then I will have a line. Does that make sense? What I'm talking about? Let's see if I can write it down properly here. So if I have a vector, and let's just stick with R2 for now. So if I have a vector v in R2, then it turns out that if I multiply this by some scalar, let me just call the scalar the t. Then t times v is going to be some vector that falls along that line, right? In fact, if I consider t as any as a range of numbers, say going from negative infinity to positive infinity, what I would get here is a set of points. If I take a look at where the head of the vector lands, I would get a set of points that would be on this line. Does that make sense? So I could define this as a function where I'm putting in different values of t, and then I would be getting a pair of points. You can look at it as a vector or any point that would be on this line. Does that make sense? So this is one way to create a line. What we have here is a line. So this is a line. Through the origin. Passing through the vector v. Okay? So any of those scalar multiples would work for this. Does that make sense? All right, so this is one way to get a line out of vectors. But the thing about this particular line is this is a line going through the origin. I wonder if it's going to be easy for us to find the equation of this line using the x and y values. Think it'll be easy? Okay, let's find a value for v. So v equals, I want to say 2, 1 again, but let's make it arbitrary. So let's make it a and b. All right. So L of t turns out to be t times the vector v, and that is equal to AT BT, right? And so it turns out that these are the x and y components. So what we could do is we can break this up to two different equations. And what we have here, actually I should have written it the other way, x is equal to AT and y is equal to BT. This is known as parametric equations, and if you've taken anything that, some pre-calculus courses cover parametric equations, and if you were to graph this, you would get an equation of a line. But I'm interested in getting rid of the t's, because, you know, when we learned equations of lines, we didn't have t's, right? So let's take each of these equations and solve for t. T equals x over a, and t equals y over b. And if they're both, this is a y, and if they're both equal to t, we should be able to set them equal to each other. So x over a is equal to y over b. And if I want to write this as y equals mx plus b business, I would solve for y, and it looks like y is equal to b over a times x. Does that make sense? Let's see if that makes sense. This is your vector v. This is the point A, comma B. Right? So what's the equation of this line going through this? The slope is the rise over run. And then the y-intercept is the y-intercept is 0, right? So to find an equation of this line, you got the slope is equal to b over a, and then the y-intercept is equal to 0, so y equals mx plus b, so b over a times x plus 0, and that's what we got from the vector. Okay, so this is a line. This is one way to take a look at a line. So t times a vector. So t times a vector is going to be a line passing through the origin. All right? Remember that. All right, let's come up with another example of finding an equation of the line. This time, something that's perpendicular. So let's take a look at another example. Let's say I have this vector v over here. And instead of a line going along the same line as a vector, let's say, what if I wanted to find a line that's perpendicular to that vector? So we just learned about the dot product, right? And the dot product of two vectors that are perpendicular is equal to 0. Okay, now let's think like mathematicians here. And consider each point on this line as some x and y. So I'm going to randomly pick a point, call it x, y. And when I randomly pick a point, it's an arbitrary point, so that can represent any point on this line. Right? So I'm going to make a vector from the origin to that point. And that vector is xy. Let's just call it, I don't know. Let's just call it xy. It's a vector xy. Right? And that's just a random point on the line. So I know that if these two things are perpendicular, regardless of what point I have on this line, that vector, the green vector, is always going to be perpendicular to the v vector. Right? So I know that v dotted with xy is going to have to equal to 0. Does that make sense? So that's it. And if we expand, let's say v was equal to, let's let v equal to ab again. So ab dotted with xy is going to be ax plus by is equal to 0. So this would be my equation of the line. So you can write it like this, or you can write it in standard form if you want, but this looks like it's an equation of a line. Yeah?
Is there any condition
Yeah, I guess if v was just on the x-axis, then that line would be perpendicular, right? Well, let's do an example like that. So what if v was 1, 0? And I want to find the equation of this line, which is perpendicular to that, but it's also a vertical line. So I think we might have some problems, or I don't know if this will be a problem. Let's see. According to this is just the vector v, 1, 0, dotted with xy, and then we set that equal to 0. So we got x plus 0 is equal to 0, so x is equal to 0. That looks like it still works. Right? That's the equation of that vertical line, x is equal to 0, right? Yeah, so this looks like it'll work for all cases. All right? Now, the cool thing about this is that we can extend this to 3 dimensions. Actually, we can extend the other one to 3 dimensions also. Let's see if we can extend it to 3 dimensions. Remember, this one is if you have a vector in R2 and then you multiply it by, just scale it, and then you'll have a line. So that seems like a simple idea that we can extend in 3D. So let's see. Let v be a vector in R3. So this is a 3-dimensional vector now. What is t times v in this case? What's it going to look like? It's going to look like a line? A plane? A line? What? I'll say a line. See if we could do it here. 2, 1, 2, 1, and let's put -3. So if I want to make this into a vector, I'll have a vector in standard position and then that's this vector right here, the red vector. The green arrows are the x, y, and z axis. Actually, the z doesn't have an arrow on it. So this is a vector in 3 dimensions. Now, what if I multiply this by a scalar? So these vectors that I'm getting, it looks like if I just multiply it by a scalar, I'm just going to get vectors, right? And these vectors that I'm getting looks like it's running along that same line. Okay? So it looks like this is just going to be a line in 3 dimensions. So let's make a note of that. So this looks like it's going to be a line in 3 dimensions in the same direction as V and passing through the origin. Or same, not dimension, but direction, same direction. Okay? So now we can have a line in 2 dimensions, and turns out we can have a line in 3 dimensions. In fact, you can have a line in any dimension you want just by multiplying a vector by a scalar. So we can have a line in 4 dimensions that we can't picture, but I can be assured that it's a line because it has this one parameter t that describes it. Okay, now we did one other thing over here that looked fairly simple, and we dotted the vector with xy, right? And then we said that that was a line that's perpendicular to this. I want to take that same concept and same idea, keeping the same vector in R3. What is V dotted with x, y? Now I have in 3 dimensions, I have 3 variables, a z as well. And is this a 0 vector or is it a 0 scalar? V dotted with a vector x, y, z equal to 0. Is that a scalar, a 0 a scalar or a vector? Scalar, because it's a dot product, right? You dot 2 vectors, you get a scalar. So this is a 0 scalar. So this is just a number. What do you think this is equal to? So think about x, y, z. As some random, this is my axes, x, y, z, and think about this vector x, y, z as some random point. Well, why don't we start by looking at this as a vector v? Sorry. Let's think about that as a vector v. And then what can I say about x, y, z so that the dot product with v is equal to 0? It's perpendicular, right? So out of all the points that I can pick, why don't I pick this one that looks like it might be perpendicular? Or I can pick another point over here that looks like it might be perpendicular. Or pick another point over here that looks like it might be perpendicular. And think about this. If I collect every single point, x, y, z, so that that vector is perpendicular, what do you think I'm going to get? A plane? Does it look like a plane? Yeah. It turns out that this will give you a plane. All the x, y, z values here would give you a plane that is going to be perpendicular to that vector v. So if v equals the vector a, b, c, then this ax plus by plus cz equal to 0 is a plane that is perpendicular to the vector v. Pretty cool, huh? So in fact, just as the last drawing here, let's take A and dot it, I guess multiply, with XYZ and set it equal to 0. I wonder if this is going to draw it. It didn't work. What? Yeah, so I guess so. All right, here. 0, 0, 0. A, that's your vector. And then, so 2x plus 1y minus 3z equals 0. So now I would get this. You see that vector? It's perpendicular to that plane. Okay? All right, so that's how you get lines and planes. And again, you can get a plane in 4D also, or 5D in higher dimensions just by using the same sort of technique. All right, see you guys next time.